the implications of that are staggering. And it's not only, of course, carbon dioxide, but a very important paper in Nature Climate Change identifies almost 470 traceable pathways for impacts on human health, water, food, economy, infrastructure, and security by multiple climate hazards, not all coming, of course, from carbon dioxide. And so what I'd like to do now in just a few minutes is to take two global sustainability agendas that much of the world has embraced and to think about how this idea of the molecular basis of sustainability might contribute to that, might contribute to sustainability science. And the first is the one that you heard about from Javier, the UN Sustainable Development Goals. We'll come back to that. 170 targets require strategies based on consideration of systems in the flow of material and energy. You can't do that without chemistry, and I think, Javier, you showed that very, very nicely. But the second is the Planetary Boundaries Framework, first published in Nature in 2009, and then a very important follow-up in Science in 2019 by the Stockholm Institute of Resilience, the work of Johan Rockström and his group. And the Planetary Boundaries Framework is an attempt to quantify, to whatever extent is possible, the threat that we have to the sustainability of our planet from human activity. It identifies 9 Earth systems: climate change, ozone depletion, ocean acidification, and the colors are important. I can't point to them with the laser here, but if you look at the blue circle in the middle, and then there's a red circle following that, every one of these 9 Earth systems, there's an attempt to quantify a control variable that describes how far out we are proceeding on that Earth system on a journey away from sustainability. And so if you have a control variable that's within the blue circle, that's considered to be below the boundary, below the planetary boundary, a safe space for humanity. And when we come to the red circle, we're now moving from a zone of uncertainty into a region of high risk. And there are, you will notice, 2 of the Earth systems where we've exceeded, we're in the red, and one of them is loss of biodiversity, and the second is the nitrogen cycle, the nitrogen and phosphorus cycle that Javier was talking about. In the latest paper in 2015 in Science, 2 of those core systems have been described as core systems, because even though this is a system and every one of the Earth systems is related to the others, 2 of them on their own have the potential to drive Earth into a new state should we not do something about it. And that's climate change and loss of biosphere integrity. And so in our Nature Sustainability paper, we've identified a flow of ideas for education about the molecular basis of sustainability. First comes from recognizing the material basis of society as being important for sustainability. Then secondly, shaping the practice of chemistry by sustainability science. Reimagining, reorienting the way we do chemistry education to move from working with very isolated facts to seeing systems, and then to do so using systems thinking. So let me try to make that concrete so that you can imagine in perhaps a first-year chemistry course what this might look like. Maybe you'll have an answer for this after Javier's talk, which might be different than the answer you would have before his talk. What's the most important technological invention of the 20th century? And many people say, maybe the computer chip. The case has been made that the Harbor-Bosch process is the most important technological invention of the 20th century for the reasons that Javier made. You might think that we got together and coordinated our presentations here. But that case has been made by a Canadian, Vaclav Smil, who says that without the Harbor-Bosch process, perhaps 40% or 50% of the world's population would not be here. An incredibly important contribution of chemistry to the survival of humanity. But yet that very important process that Javier talked about might also be thought of as a failure of systems thinking. And I say that because if you think of 100 nitrogen atoms produced in that Hабербаша process in the factory in the form of ammonia, and you look at following those nitrogen atoms all the way through the chain until you eat a hamburger, you find that 96 of those nitrogen atoms are lost. And if you're a vegetarian, the situation is only a little bit better. 86 of them are lost. So we have failed, as we have this wonderful technology to give us nitrogen atoms for our bodies, we failed to do that in a way that considers this as a system. But this is also, I think, a failure of systems thinking in chemistry education. You might imagine, and maybe your situation is different in Russia, but in North America, every first-year chemistry text in university has the Hабербаша reaction. And it looks something like this. There will be a reaction shown in a chapter on equilibrium, even though, as you've heard, it's mainly kinetics and catalysis that's important. And there will usually be a little sidebar that says, Fritz Haber was a German chemist. He received the Nobel Prize in 1918 for his invention of the Hабербаша process to make ammonia from nitrogen and hydrogen. He called it making bread from air. And then you look at how a textbook develops this idea, and usually it's limited to equilibrium calculations. Can you change the concentration of nitrogen? What happens to the amount of ammonia? And so on. No connection is usually made between the Hабербаша process and the survival of 50% of our planet on the one hand, or the threat to our planetary boundary from the fact that we've fixed too much nitrogen on the other hand. So a failure of systems thinking in chemistry education. So what might we do about that in chemistry education? And think whether there are some ways in which, in your own teaching, if you're an educator, you might be able to do this. And the analogy I like to use is if you have a cell phone, you can zoom out. So you can take this theater where we are and you can go to Google Maps and you can zoom out, and pretty soon you can see this complex and this university in the context of Russia and in the context of our planet. We can look at the whole and then we can zoom in and look at part of it. So we've developed some tools on the project to visualize the interconnections among system components. And we call these systems-oriented concept map extensions. Okay, I'm sorry if we had a translator here, the translator would be pulling her hair out. It's perhaps difficult to find the right language for this, but it's a concept map, and it's showing the relationships, the interconnections among system components. And we picked that name because it has a nice acronym, SOCME. So we've developed SOCMEs to visualize these interconnections, and these ones that I'm going to show you have been drawn by Tom Holm, a project member. And the idea is to be able to zoom out to help students see the whole, but then to be able to take a part of it after they see the whole and define some boundaries, which then become the focus of study for a particular unit. And this can help us see emergent behavior change over time and cause-effect relationships. So let me illustrate with the Hабербаша process. So this is what has been done in the chemistry textbook that I was taught chemistry from. There's a simple reaction, N2 plus H2 gives ammonia, some calculations based on that, and that's the extent of what students learn. So with a system-oriented concept map extension, one can say, okay, how could we see that by zooming out? What are the other dimensions to that? And one of them, of course, are the reaction conditions that are needed to make ammonia. It requires a catalyst, it requires temperature above 350 degrees to form ammonia at a practical rate. And so now we've expanded the system to look at the reaction conditions. And there are topics here now that could be considered in another section of the course that deals with equilibrium and kinetics. What about the chemical inputs? You've heard about that again from Javier. So the hydrogen and the nitrogen are generally produced unsustainably now. Work done by a colleague at Dalhousie University in Canada. The hydrogen starts from methane in the steam reforming process. It comes from fossil fuels. And to produce 1 kilo of ammonia requires the consumption of 3 kilos of methane and produces 3.5 kilos of carbon dioxide.